programmable gate arrays. So the idea is, we talked about a system on chip, and we said that system on chip is basically getting different intellectual property components and combining them into a single chip. The process was very difficult in the old days, but nowadays you can just call the vendors and ask them for the parts, combine your system, build it, and start selling your devices. Now there is another area in which this is very important, which is the area of field programmable gate arrays. So instead of going for application specific ICs, and we said that an application specific IC is quite expensive and it takes long time to fabricate, we nowadays go for field programmable gate arrays, which are an FPGA. So today we are going to talk about FPGAs and see how FPGAs are dealt with in an embedded system. The programming and dealing with FPGAs, you will see that it's done all on VHDL. So you can program an FPGA using VHDL, which we have studied in the previous year, in the previous semester, sorry. So today we are going again to talk about the FPGAs, and here it is in module 4, 12, So FPGA, field programmable gate array. Field programmable gate array. So the objectives is to understand what is an programmable logic, then what is an FPGA, the structure, special functions, comparison, and usages. Then we are going to talk about the Altera Cyclone 220 FPGA. By the way, these are the same ones we have in the lab for programming the VHDL. Then we will talk about a little bit about design flow. Now, when it comes to semiconductor chips, you all know how a chip looks like. It's just a small circuit inside here, and these pins are basically connected to the chip. So what's more important is over here, what's inside the silicon chip. Now, this silicon chip can be a microprocessor or a microcontroller, and we saw how microcontrollers in level 3 and in the previous first part of embedded systems, how microcontrollers are dealt with in terms of FPGAs, in terms of ICs, or it can be an application specific IC. These application specific ICs are basically a totally different story. So you can have an IC that will do digital signal processing, or an IC that will do any function that you want. And finally, these can be either an FPGA or a CPLD. Now, these are the different types of semiconductor chips that we deal with. And today we are going to concentrate on the field programmable gate array. So programmable logic, if you remember the PLA, we have studied the programmable logic array when we tried to design our ROM in level 2. In level 2, if you remember, we had a ROM design in which we used a programmable logic array. The programmable logic array, basically, instead of having a a decoder in our design, we removed the decoder and we said we will use a programmable logic array. It's just like using a lookup table to get our circuit. Instead of having to build the digital circuit, we can build a lookup table for that. So an integrated circuit can be reprogrammed with a digital logic of a certain level. Started at the late 70s and continuously growing. Now available of up to approximately 700,000 flip-flops in a single chip. Now, why flip-flops? Again, flip-flops are sequential circuits. flip-flops can be used to store values, and usually we talk about the D flip-flop. And it's very important to work with the flip-flops because they can hold the data for a long time. They can hold data for a long time. So the advantages of programmable logic are short development time, reconfigurable, saves board space. Remember, it's just like talking about something that you can program. If it's something can be programmed, then it's no need to worry about the development time of the IC. If there is a mistake, you can reconfigure it. It saves space on the board since it's very easy to program. Flexible to changes. No need for application-specific expensive design production, because all we have to do is run our simulation, then and program it. Fast time to market. Bugs can be fixed easily. Why bugs can be fixed easily? Because if there's a problem, you can fix your code, then reprogram your IC, and off-the-shelf solutions are available. Similar to what we had seen in microprocessors, we have different families of field programmable gate arrays, and these families make things and make our life very easy because we can easily reconfigure and choose which IC we want to use. So this is our programmable logic array. If you recall this, we studied this in level 2. We had here it's 3 inputs, here 4, 2. So this is a 3 by 4 by 2 PLA. And we talked about this PLA earlier in level 2. We said instead of building a digital circuit for this, we just build a circuit in this way. So all we have to do is choose the PLA size and fuse the outputs as we want them. So the first programmable device, it's a 2-level or structure, one-time programmable. This is the first one. Remember, all we have to do is just to fuse, put these X's over here. So if I put an X here, an X here, an X here, it will give me C complement B A. So this is the first value. Over here, it is A complement B C. Over here, it is A complement and B complement. Over here, it is A, B, C. So it's quite simple, and then afterward we use an OR gate to combine all the structures that we need. Remember, when we deal with FPGAs, or sorry, with PLAs, programmable logic arrays, we do a Karnoff map simplification based on or with the aim of simplifying the two functions at the same time. Now, the simple programmable logic device or complex programmable logic device, in the simple programmable logic device, we have a single AND level, then a flip-flop and feedback. So this is your FPGA, then you send it to a flip-flop with a feedback. In a complex design, we have several programmable logic devices stacked together. See, this is a programmable logic device, programmable logic device, programmable logic device. We have them all together, and we have a complex programmable logic device. This is the simple one. This is the complex one. In the simple programmable logic device, we have the single AND level over here, and then you have a flip-flop that will give you a feedback to the circuit. In a complex programmable logic device, basically we have the programmable logic devices stacked together. So you will have more and more programmable logic devices, and in the middle you will have some sort of buses and connections between these programmable logic devices. Now, these programmable logic devices we will be talking about them and calling them a lookup table. Now, inside an FPGA, this is the element over here. I think this line needs to be corrected. Wait, needs to be red, and this one I will make it red. Okay. So, in an FPGA, which is this device over here, you can see the following. we can see the logic elements. Okay, so the programmable logic blocks are logic elements. So these green are our logic elements, and the connecting switches are the yellow elements. These are the yellow elements. So the the logic elements implemented combinational or sequential based on a lookup table. طيب, now what is a lookup table? Lookup table, if you have a very big function, instead of programming the function, you build a table for it. You will know that if I put an input, okay, if I have a lookup table, something like this, it's a table, and let's assume we have the inputs A, B, C, and this is our function. Then we have 0, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0. Okay, so this is 1 also. Sorry, this is 1. So you have a function. Okay, instead of going and building a circuit that will do this function, which will need the following: you need to simplify the circuit, you need to build the digital circuits. No, go and build a lookup table. Say that if I have this input, I will get this output, like using a decoder. So we build a lookup table which will have the inputs A, B, C. Once we have the inputs A, B, C, we get the output. This is a multiplexer D. Okay, these are all options. We have a clock and we have a reset. Now, in this logic element over here, you will have this value over here. So basically, this is one logical element. This is one logical element. This is one logical element. So each function is basically built out of a lookup table. Well, lookup table makes things much more easier and faster. Instead of going into the details of building the digital circuit and the complexity of building a digital circuit, we can simply build a lookup table for that. So the logic element is basically a lookup table with a D flip-flop. طبعا D flip-flop basically, if the input over here is of the clock is 0, the output will remain the same regardless of the output. So D flip-flop, I need an empty page. So where is, okay. So D flip-flop, you will have your input. We have D, clock, and Q. We have the clock. I don't know why it's doing like that. Then we have D, and we have our output. Okay, now the table looks something better. So we have the clock. If the clock is 0 and the D is whatever, the output will remain no change. Okay, now if the clock is 1, the output is D, the input is D, the output will be D. So D flip-flop basically will do what? If there is no clock, no change on the output. If there is a clock, then whatever is at the input will be available at the output. هاي شغلة D flip-flop. احنا مرات we call it the D latch. We call it sometimes the D latch. Latch, something that holds. Okay. So a D flip-flop is used to hold the output. Now we have a programmable input-output block, which is this in red, which is configurable input-output for external connection supports and tri-states. Tri-states, if you recall last time we talked about tri-states. Tri-states is the option of having an open circuit in our design. Then we have programmable interconnected wires or interconnections, which is these yellow things. These wires to connect inputs, outputs, and logic blocks. They have the clocks, short distance for local connections and long distance for distance connections. Now our lookup table is a RAM with data of width 1. This is an example of a lookup table. The contents are programmed at power up. So for example, if I have this logical function as my circuit, I can build it using a lookup table like this. So this is my truth table, and my lookup table will be something like this. So this is my output. My output will be sent to a multiplexer, and the inputs will be used for a selector for the multiplexer. Instead of building this circuit, we build up this circuit. Now you will say this one is easier, but this one is faster, because here your signal will have to travel. Here your signal will go immediately to the output. This is one option. The other option, if this circuit is complex, then it will take more space and will consume more power. But over here you can see, even if a circuit is complex, we don't care about actually the circuit. We only care about the output, and we multiplex it to get our desired output. So this is basically the programmable lookup table. Now special FPGA functions. The FPGAs, and especially from Altera, and if you recall Altera, we have used it in our VHDL programming. It has an internal SRAM, an embedded multiplier, and DSP blocks, embedded logic analyzer, embedded CPUs, not CPU, CPUs, high speed input output, up to 10 gigahertz, DDR, DDR2, DDR3, SDRAM memories, and phase lock loops inside this device. Remember, we are talking about an IC that can be used to power up a phone. Remember, we are talking about an IC that can have a Wi-Fi, Bluetooth, a GSM connection with some digital processing, and these things, all of them available into a single IC. Now, in comparison, when you talk about the three types of systems that we can deal with, we have the processor, we have an FPGA, and we have an application specific IC. In terms of flexibility, the more flexible device is the processor, which is a general purpose processor. Second comes the FPGA. And finally, the application specific IC is the less flexible, because once you program it, you cannot change what's inside it, so it's considered not flexible or no flexibility. When it comes to power, speed, and efficiency, the CPU sits at the end. The CPU has the less power efficiency and the less speed. طبعا you will tell me the CPU is very fast. Yes, CPU is very fast, but the CPU will not do the job in a very fast way in compared to these two, because they are intended for specific applications. But a CPU is a general purpose processor. You will not connect your CPU to an airbag system or a car safety system. You will not connect your CPU to a fire alarm system, because the CPU is too slow in these applications. However, FPGA comes also in the middle. In terms of speed, it's faster than a CPU, but not as fast as an application specific IC. In terms of power efficiency, again, it comes in the middle. Application specific IC, yes, it's not flexible, but it has a single application, and when it comes to speed, it's very fast and very power efficient. But this comes at the cost of being a flexible system. So there is always a trade-off when it comes to engineering and thinking about devices. So an application specific IC is basically not flexible but very fast and very power efficient, whereas a processor is very flexible but it has very less speed and it is power hungry. Again, when I say it's not fast, it's in comparison with FPGAs and application specific ICs. Okay, يعني don't say that we are saying the CPU is not fast. No, the CPU is fast. The CPU is actually very fast. If you give it one task, it will be better than both the FPGA and application specific IC in terms of speed. But for a general purpose, the processor is not fast as the application specific ICs or the field programmable gate arrays. Now the usage is digital designs where the application specific ICs are not commercial. Sometimes you build up your design, you want to start sending the design up to out to the manufacturers. You have two options. You have the option of spending hundreds of thousands to build your application specific IC, or you go and buy an FPGA, program it. If it works, start sending your design based on FPGAs. It's reconfigurable systems, it's upgradable systems, application specific prototyping and emulation. Many companies, when it comes to application specific IC, before going to the application specific IC stage, remember, application specific IC is very expensive. To go into that stage, it will cost you a lot of money. So instead of going to that stage immediately, many companies, they tend to do what? They tend to do the prototyping of application specific ICs on a field programmable gate array. Now this will help a lot in the design and will cut the cost of designing a lot. The final application is education. In the lab downstairs we have a lot of FPGAs that we can use for programming. Yes, they are a little bit old and they need old computers to program, but still they are available and we can use them. Many manufacturers such as Agilent, Altera, Lattice and Alcatel, they build application specific FPGAs. Usually we go for Altera, which is the one we use in our microprocessor and microcontroller lab. This is the Cyclone 220, which has 18,752 logic elements. It's equipped with 52 M4K RAM blocks, and I'm going to talk about these M4K RAM blocks. It has 240 kilo total RAM bits. It has 52 9x9 embedded multipliers. It has 4 phased lock loops. It has 16 clock networks, 16 net clocks, okay? It's not one clock. It has 315 user input output pins, and it's SRAM based volatile configuration. Yani we are talking about a very powerful system. We are talking about a very powerful element. So this is the Altera Cyclone 2. And if we want to check the price for an FPGA, we can go for Altera Cyclone. It will cost you around 10 reals, 21 reals. This is Arduino Altera Cyclone. See this one. Similar to an Arduino board, and you can see that this is an FPGA chip, and you can buy it and you can program it and use it. So this is one option. Let's check this one out. This one also on eBay. This is the same one we saw. It will cost you around $28 US, and there's no zooming in. Oops. You can see here it's the Altera Cyclone chip, quite similar to the chips we are used to see in Arduino. It looks something like the Arduino chip, but this is an FPGA, and we can see it's an Altera EP2C5T114. It's a development board. If you want the Cyclone 5, this is the Cyclone 5. It's $14. It's not that much. For this specific IC, we can find a lot of components. See, $14. So in general, what I want to show you that it's not expensive to buy an FPGA. Now, when we talk about M4K memory, the Cyclone 2 devices features with an embedded memory structures to address on-chip memory needs of an FPGA design. The embedded memory structure consists of columns of M4K memory blocks that can be configured to provide various memory functions such as RAM, first in, first out buffers, and ROM. The M4K memory blocks provide 1 megabit of RAM at up to 250 megahertz. Now, what do we mean by M4K? M4K, basically the maximum performance is 250 megahertz. Okay, the total RAM bits is 4608. So the configuration, it's either 4K by 1. That's why it's called memory 4K. It's either 4K by 1 or 2K by 2. Remember, if I multiply these two numbers, I will get this number. So 4K multiplied by 1 is this one, 2K multiplied by 2 is this one, 1K is multiplied by 4 is this one, 512 multiplied by 8, 512 multiplied by 9, 256 multiplied by 16, 256 multiplied by 18, 128 multiplied by 32, or 128 multiplied by 36. Let's check 128 multiplied by 36 is equal to 4,608, and if it's multiplied by 32, it is 4,069. It depends which type of bus width you are willing to use. If you are going to use 32 or 36, depends on the application. So this is what we mean by M4K. This is what we mean by M4K blocks. You can configure them as you want for the data size that you intend or you need. So this is the Cyclone 2 internals. You can see these are the embedded multipliers over here in gray. These are your input-output elements in brown. These are the phased look loops, as you can see in the corners, and they appear in the corners, 4 phased look loops. Here are the logical arrays, and in red are our memory blocks as we need them. So basically this is the design of an M4K FPGA. So the Cyclone 2 logic array is built of logic array blocks, and you can see the connections being we call it interconnected because everything is connected to everything. You can see over here this is a row interconnection, this is a column interconnection. These are the links of interconnection from adjacent blocks over here. This is a direct link to adjacent block. This is a logic array block, and it's all interconnected as you can see over here. This is just for your information. This is the logic array block, this one. How it looks from inside, it will look something like this: logic element 1, logic element 2, up to logic element 16. It has 16 logical elements. Each block has 16 logical elements. These logical elements are locally interconnected through these lines over here. Register chains and logic array blocks control signals. We have the clock, two clock enables, asynchronous clear, synchronous clear, and synchronous load. All of these are available inside your logical array block. This is a logical element block diagram, just to show you how a logical element looks from actually inside. You can see previously we talked about the lookup table. This is our lookup table, and this is our selectors over here for the lookup table, and this is our D flip-flop. It is similar to what we checked over here, but not here even. This one, where you have a lookup table with a D flip-flop, but this is again a more complicated or complex scenario. This is the logic element in normal mode, and this is the logic element in arithmetic mode. Depends on the type of mode you are using. So for normal mode, it's suitable for general logical applications and combinational functions, whereas for the for the arithmetic is ideal implementation for adders, counters, accumulators, and comparators. طبعا all of this is not memorizing, it's just I'm telling you information. If you are going to ask me how we are going to get this in the test, it's just maybe general questions about the FPGAs. Now the Cyclone 2 features, we have in, out, and tri-state. Tri-state means open circuit, different voltages and input-output standards, flip-flop options, pull-up resistors, direct double data rate interfaces, series resistors, bus keepers, driver strength control, slew rate control, single-ended differential inputs and outputs. So this is how a buffer in Cyclone 2 will look like. This is the clocking of a Cyclone 2. You can see here the 4 phase look loops, which are very important to look a signal. And we have the clocks, different clocks. You can see over here different clock signals for the circuits. We have 16 global clocks and 4 phase look loops inside the Cyclone 2, which is quite a little bit old. This is the phase look loop inside the Cyclone 2. And in terms of memory, we talked about memory and we said we have different types of memory, which is the M4K memory. And this is the Cyclone 2 memory structure. This is the Cyclone 2 multipliers and how they operate. This is the frequency delays and how we calculate the frequency delay. It's a total it's a lot of information involved when it comes to the delay of a system, to calculate how much time it needs for a signal to propagate from the input to the output of the system. This is the design flow. Usually you check your specifications, then you choose your HDL language, then you do your design and your programming. These are some design rules for application specific ICs and FPGAs. This is just information also. I'm not going to go into much details over here. Basically this is all we have for FPGAs.